points, that is A1, B1 to A2, B2, and so on. So suppose we are taking any curve y equal to f of x in xy plane. So I can say, suppose we are taking this type of, this is xy plane, and suppose we are taking a curve on xy plane, and if you are denoting 2 points P and Q, that's the arc of the curve. Okay. So suppose you're finding the arc of this PQ or arc of this curve PQ on the curve or on the xy plane, and we can use the triangles, right angle triangles that can be formed by using the arc. Suppose you are taking a line here, that is a horizontal line, is a vertical lines, and this is a horizontal lines, and we can make just a triangle type of structure here to find the value of the curve or value of the arc of the curve PQ or arc PQ. Okay, so if you think here, this dx and dy are so small, then this arc PQ be just similar to a straight line PQ. Okay, since we are assuming this dx and dy are so small. So if we use the triangles rule here, so you can write here this h ds square, since we are assuming this PQH, the arc PQ, ds square, that's equal to dx square plus dy square. Okay. So this one, ds square, that's equal to dx square plus dy square. Upon simplification, we can write this as ds by dx whole square, that's equal to 1 plus dy by dx whole square. And if we find ds by dx, it becomes root over of 1 plus dy by dx whole square. Or this is the arc length S, that can be denoted as root over of 1 plus y square dx. So this is the arc length. Okay. And suppose next we define the surface area of revolution. Means before that, we just discuss the volume of revolution, then we go for the surface area of revolution. Suppose we are taking a curve on xy plane, and if we are taking an element, or first we are taking a small part of this curve AB, that small cross section, that is PQ, and if we draw a vertical line from P and Q, okay, then we can find an element that's of the form of PQ. Let it be suppose P1 and Q1. This is the element that we can get here. Okay. Suppose someone want to rotate this element around this axis, x-axis. Then you will see what we will get about the volume that we will get after rotating PQ around x-axis, because here it's a volumetric area. If we rotate, it will just gives you a volumetric type of disk. Okay. If we singly rotate this P around this x-axis, we can find a circle-like structure. And if we rotate this PQ with the inclusion of this area, then we can get a volumetric area after a rotation about the x-axis. So here you can say, let P be the point, that is xy, and Q, because we are taking this P and Q are lies close to each other. So this is the point x plus dx and y plus dy, where you can say this dx and dy are so small. Now, if we see from this figure, you can say the volume of the disk that can be formed after rotation about x-axis, it becomes pi y square dx, because the radial distance of this disk be y, because it's parallel to y-axis. So you can say this is the volume that you can find after rotating this PQ around x-axis. Okay. So this is the volume of the disk, and the volume of the revolution of arc AB, this arc AB, about x-axis. Okay. First we have considered this one, this PQ, and if we finally try to find out the whole volume of this arc after rotating about this x-axis, so you just imagine it will just give you a funnel-like structure after rotating, and the volume of revolution that gives you A to B this pi y square dx. Our integration ranges from a to b pi y square dx. So what is a and b? A and b are any 2 points on the arc AB. Okay. So where you can say this a and b are the abscissa of a and b. Similarly, if someone consider what happens if we rotate this element PQ around y-axis, in that case, your volume of the disk be this is pi x square dy, because you are rotating about y-axis, and the radial distance that is parallel to x-axis. So in that case, you can write this one volume of the disk is pi x square dy, and the volume of revolution of this arc AB around y-axis, that gives you pi, let it be c to d x square dy. Okay, so this is about the volume of revolution around an axis. Either it may be x-axis or it may be a y-axis. Next, we go for surface area of revolution. That means here we have considered in the last section we have considered the volume of revolution. That means we are considering this volume. Okay. And in the third part, we'll consider surface. That means the surface area that lies on the disk, or we can say that lies over the solid disk. Okay. So here, correct. Similarly, when we find the surface area of revolution, we can go for this picture here. This is the arc of the curve, whatever the curve C. This is the arc AB. Here also we are taking the same two close point P and Q. This P point be xy, Q point be x plus dx, and y plus dy. Okay. Now here in the previous case, we are finding the volume after revolution of this element around the x-axis. But here we just consider the surface area of the disk after rotating about x-axis. So here we can say, if we find the surface area of the disk formed by the PQ or formed by the arc PQ around x-axis, it becomes 2 pi y ds, not dx, ds. Okay, where s be the arc length or ds be the arc length of PQ. Okay, so if we find the value of ds using the first arc length formula, so here we can write this ds equal to ds by dx into dx. We know the value of ds by dx as root over of 1 plus dy by dx whole square into dx. So we can substitute this one here in dx. Okay, upon substituting, it becomes 2 pi y root over of this one into dx. Now, if we consider the whole arc AB, and if we try to find out the surface area of revolution of the whole arc AB around x-axis, in that case, we can write the surface area of the solid, that is 2 pi y, because this 2 pi y dx, that ds that we have obtained from PQ, and since we are taking the whole part of arc AB, so we are considering integration ranges from A to B, 2 pi y root over this one into dx. So in this case, it will give you the surface area of revolution of this whole arc AB around x-axis. If someone want to find out the surface area of revolution around y-axis, then also you can find out. Okay, so this is the actual idea about how to find out the arc length and how to find out the volume of revolution of a solid, and similarly the surface area of revolution around the axis. Okay, but in our problem, we have to find out the extremal value of that surface area of revolution or volumetric area of revolution, or whenever we are assuming any 2 points between 2 points on a surface or on a curve, and if you try to find out the distance between this or minimum distance between these 2 points A and B, in that case, we can use these extremal problems. So suppose we are finding the minimum surface of revolution. So what is our objective here? We have to find out a curve that passing through 2 points, this A and YA and B and YB, such that when it is revolved about x-axis and it generates a minimum surface. Okay, because if we see here, if we rotate this arc AB around x-axis, you can get different type of surface after the surface area of revolution. Okay, first you can find out a surface from A and close neighborhood points up to B. You can get many surface, but our basic aim in the extremal problem is we have to find out a minimal surface that can be formed after the surface of revolution of the arc AB. Okay, so to find a curve passing through 2 points, this AYA and BYB, such that when it is revolves about x-axis, it generates a minimum surface. So what we have to extremize here, either maximize or minimize, because the problem is minimum surface of revolution. So we have to minimize here. This is the surface area of revolution that we have got from our formula 2 pi a to b y into root over of 1 plus dy by dx whole square dx. So we have to minimize this surface area of revolution. Okay. So for minimization, we can use Euler's formula to get a minimization or minimize curve. So here f is this y into root over of 1 plus dy by dx whole square. And as you know from Euler equation, if it doesn't contains either x or y, we can use the similar formula or the short formula. So here, since f is independent of x, we can use the Euler formula, this one, f minus del a by del y dash into y dash, that's equal to constant c. Okay. So upon simplification, here we can write this h, this f, that is y into root over of 1 plus y dash square, minus, if we find the del a by del y dash, that gives you y divides root over of 1 plus y dash square into y dash. This y dash, that's equal to c. Now, if you further simplify this one, you can get the equation like this: y equal to c into root over of 1 plus dy by dx whole square. Okay, upon further simplification, this becomes y dash equal to 1 by c, this one. And if you write this one as dy by dx equal to 1 by c root over of y square minus c square. Or you can write this dy divides root over y square minus c square, that's equal to this dx that can be taken to the right hand side. So you can write dx by c. Okay. Upon taking the integration on both sides, we can find here this one as cos hyperbolic of or cos hyperbolic inverse of y by c, this one, and this one x by c plus c1. Okay. And the value of yb, that is c cos hyperbolic x by c plus c1, which is a catenary. That means if we minimize the surface of revolution, we can get a curve that looks like a catenary. Okay, this is the minimal surface that can be obtained from this surface area of revolution of the arc AB around x-axis. Okay. Here we have fixed up 2 points also. These points that can be fixed up like this. Suppose here this point be AYA and this point B BYB. Okay, we are just rotating the surface area around x-axis, and we are just trying to find out a minimum surface area of revolution. And here we can get the minimum surface area of revolution, that is at this one. And since this y equal to c cos hyperbolic, there is a presence of constant here, we can say, so whatever the minimal surface, it's a general solution. Okay, we are not taking a single just a circle-like structure or single catenary here. It's a family of catenary. Okay, if we join this family of catenary, we can get a catenary here because there is a presence of c here. Or if there is no c present here, it only gives you a single curve. Okay, and since we are dealing with the surface area of revolution, so it gives you a catenary-like surface here. Similarly, if someone try to find out the shortest distance between 2 points x1, y1, okay, suppose you have given a xy plane and there are 2 points present in the xy plane. One point be x1, y1, another point is x2, y2. You can draw many lines between x1, y1. Either it may be a curvical structure or finally you can take a straight line also that can connect x1, y1, x2, y2. Okay. Our basic objective here is we have to find out a minimal distance between the point x1, y1. Okay, you can imagine how many lines or how many curves you can draw between the points x1, y1 and x2, y2 in the xy plane. Okay, so let us start from this one. We are just since we are finding the shortest distance or minimal distance between the 2 points x1, y1 and x2, y2, so we can use the arc length formula here, and that we have to minimize that arc length here. Okay, so since we know the formula of arc length is as equal to this one, root over of 1 plus y square dx, and we have to minimize this one to get a minimal distance between the point x1, y1 and x2, y2. Okay. So here you can see this is the value of f, which is independent of y. This is small y, sorry. And if we use the formula for Euler equation, that is del f by del y is equal to c when f is independent of y. And here, upon using this del f by del y is equal to c, you can get here y dash divides this one. And upon simplification, y is equal to c1. And upon finding the integration, it gives y equal to c1x plus c2. So what we can say, whatever be the number of lines or curve you are drawing for joining the points x1, y1 and x2, y2, finally we can say the shortest path is the straight line that connects x1, y1 to x2, y2. So that is the minimal distance that connects x1, y1 and x2, y2. So here you can say y equal to c1x plus c2 is the required curve, which is the straight line through the given points. Okay. Now the question is that here also we are getting a general solution. Now question: if you are given this is a finite point and this is a finite point, so that if you are given some conditions here, you can get a single line that can connect your points x1, y1 and x2, y2, because there are no conditions given here. So we are just getting a general straight line that connects the point x1, y1 and x2, y2. So this is the basic objective of this extremal problem, where we are just trying to find the minimal distance between 2 points, or minimal distance of minimal surface of revolution, or minimal volume of revolution, and so on. I will give you some examples also so that you can try it. Next one. Now we proceed to our functional problem. So in the last class, we have studied the functional that contains one dependent variable or more than one dependent variables. Okay. So here we are just taking here a functional involving 2 independent variables. Okay. In last class we have taken only 1 independent variables, but we have exceed the dependent variable, and in one sense, other sense, we have taken the higher derivatives also. That means in first class we have taken f of x, y dash dx. In second class we have extended that first order derivative to higher order. That means f of x, y dash, y double dash up to yn. Okay. So in next we have extended the number of dependent variables. But here what we try, here we just try to exceed the number of independent variables. So here we can say here this y is not a dependent variable. This x and y both are independent variable, rather than this z be a dependent variable. So here we consider more than one independent variable. Okay. So the functional like this f of x, y, z, this del z by del x, del z by del y, since we are dealing with more than one independent variable. Okay. One independent variable leads to ordinary derivative, and more than one independent variable that leads to partial derivative. Okay. So let us assume that a function z equal to z of xy, since we are considering here the dependent variable as z. So here we have the unknown functions that we determined, or that extremize this functional, that is z of xy. So here we can say, let us assume that a function z equal to z of xy that yields an extremum of this functional 1. Okay. Next, we have to assume this one also, since I already told in last class also, we have to consider boundary value problems or boundary points to extremize any type of functionals. So here also we can say, also we assume this Z, assume prescribed value on the boundary of the domains, not on the initial points. Okay. So these are the two assumptions. This is the function Z, which gives you an extremum, and this Z also assumes the prescribed value at the boundary points of the domain D, where this functional is defined. Okay. So if you try to find out the Euler equation of this functional one, you can find out this one. I will give you the detail of derivation also in later class. While we are while we'll find the error also. Okay, so here I just directly write the Euler equation, but I'll give the proof also how to find out this one. So here we can write the Euler equation like this. This is del F by del Z minus del by del X, del F by del ZX minus del by del Y, del F by del ZY, where this ZX, that is del Z by del X, and this ZY, that is del Z by del Y. So this is the Euler equation which is associated with this functional one, and it can be helpful for finding the extremum for the functional one. Okay. Similarly, if you exceed the number of derivatives here or order of derivatives, here we have taken the derivatives up to order 1. If we exceed the derivatives from order 1 to higher, we can write like this. This one is above x, y, z, del z by del x, del z by del y. This one del 2z by del x square, del 2z by del x del y, and del 2z by del y square dx. Okay. Suppose here we just give some notation for del z by del x and del z by del y, del 2z by del x square, del 2z by del x del y, and del 2z by del y square. These are the notation. Let p equal to this one, q equal to this one, and r equal to del 2z by del x square, s equal to del 2z by del x del y, and t equal to del 2z by del y square. Then we can write the corresponding Euler equation for this functional 3h like this. Okay. Here also we have to consider the alternate sign. Okay. In earlier, where we have taken only one independent variable and higher order, in that case also we have taken alternate side while we are dealing with higher order derivatives. Here also, since we are dealing with higher order derivatives, we have to keep the alternate sign. So this first one minus, second plus. If we go for third order derivative, we can put up here minus sign and so on. So here the relevant Euler equation here, del F by del Z minus del by del X at P. Here P be del Z by del X and del by del Y of FQ. That means this del by del X here, the differentiation with respect to del Z by del X. Here you can say here del by del Y of Q, del 2 by del X square F R, del 2 by del X del Y F S, and del 2 by del Y square Ft, that's equal to J. Suppose we are taking an example here. Find the extremal surfaces of the function. Okay. So this is the functional. So we are taking the functional as del Z by del X whole square plus del Z by del Y whole square dx dy. If we try to find out the Euler equation of this functional, we can write the Euler equation H like this: del 2z equal to del 2z by del X square and del 2z by del Y square. You can see this Euler equation be equivalent to a harmonic type of equations, and if we find the solution of this harmonic equation or a Laplace type of equation, we can say here. So if we find the solution of this harmonic equations, you can get the solutions which are looks like harmonic functions. So here you can say the extremals are harmonic functions. I'm not considering the solution because now you are just studying the solution of partial differential equation. So we are not considering the solution of this extremal problem while we are dealing with partial type of differential equations. Okay. Only here we are just trying to find out the extremal of the functional by using the Euler equation only. And here you can conclude whatever the extremals we are getting that looks like harmonic functions. Okay. Similarly, if we take another example, that is del z by del x whole square del z by del y whole square plus 2z f of xy dx dy. And if we try to find out the extremal of this functional, you can get like this. This is del 2z by del x square plus del 2z by del y square, that's equal to f of x square. And if we think about the type of equation here, you can see it's a Poisson's type of equations. Okay, it's a Poisson's equations. And if we find the solution of Poisson's equation, that gives you the extremals of these variational problems. So here we can conclude the extremals are the solution of these Poisson's equations. Okay. Similarly, if we take another example, here we have considered higher order partial derivative, that is del 2z by del x square whole square plus del 2z by del y square whole square plus 2 del 2z by del x del y whole square minus 2z f of xy dx dy. So here we can consider this total as f, that is del 2z by del x square whole square plus del 2z by del y square whole square plus this one. And if we try to find out the Euler equation for this functional problem using this formula, this one, okay, you can get the solution like this. Del 4z equal to del 4z by del x4 plus 2 del 4z by del x square del y square plus this one, which is a biharmonic equation. And if we try to find out the solution of this biharmonic equation, that gives you the extremal of this problem. Okay. So this is all for today's class, and we will proceed further. And today I will give you all the 3 lectures notes so that you can give idea about the basics of Euler equation as well as the basics of extremals, how to means why you are finding the extremals and how to find the extremals that you can get. And from next class we'll go further. So how to apply these extremal problems to various type of differential equations also, and how to deal when there are given more than 2 functionals and we have to find out the extremals of these functional problems. That means which contains more than 1 functional. That we'll discuss in later class also. Okay. Now, if you have any type of query, now you can ask. Otherwise, I will send you the lecture note today. Okay. If no question, then we'll discuss the